Hi guys, today we are going to study energy exchanges in an intrinsically coupled system. Our coupled system will be a double pendulum and connected by a spring. And my question is, double pendulums are crazy? Basically, we are going to consider, as I told you, a coupled oscillator. We are going to derive the Lagrangian equation, the Lagrangian of the system. Then we are going to write down the Hamiltonian. Next, the Hamiltonian equation motion for this double pendulum, and I would like to show you several numerical results which shows how the energy changes between the pendulums. There is, there are two pendulums, so the total energy of the system will be the energy of the first pendulum plus the energy of the second pendulum plus the energy in the contained stored in the spring. So let's move on to the question. So let's show you. Here is the sketch of our problem. There are two pendulums. The first pendulum mass m1, length l1, and the vertical displacement is θ1. The second pendulum has length l2 and mass m2, and the vertical displacement will be θ2. Actually, L1 is equal to L2. The spring, the system, the two masses, two pendulums are connected by this spring, and the deformation of the spring is given by this is x1 minus x2, where x1 will be L1 times sine θ1, and x2 will be L2 times of θ2. So let's show you. This is a sketch of the height, the vertical change in the height of the pendulum, and this is the Lagrangian of the system is defined in terms of the coordinates, generalized coordinates θ1, θ2, θ1 dot, θ2 dot, and time equal to the addition, the total kinetic energy minus the total potential energy. The total kinetic energy will be the kinetic energy of the first pendulum, first mass, equal to a half times m1 times l squared, the derivative of θ1 with respect to time squared. Similarly, the kinetic energy of the second mass will be a half times n2 times l squared times the derivative of θ2 with respect to time squared. The potential energy of the first pendulum will be the mass of the first mass m1 times the acceleration of gravity times l times 1 minus cosine of θ1. Again, the potential energy of the second pendulum will be, instead of this m1 will be n2, and instead of θ1 will be θ2. And the potential energy of the spring will be 1 divided by 2 times the spring constant times L squared times sine of θ1 minus sine of θ2 squared. Now, in order to obtain the Lagrangian, we just need to substitute expression 6, 5, 4, 3, and 2 into the definition of the Lagrangian, and we will get the Lagrangian of the system. This is the Lagrangian of the system in this case. Now, let's move on to the Hamiltonian. The Hamiltonian of the system will be h delta by h. It will be dependent of the generalized coordinate θ1, θ2, and the generalized momentum p θ1 and p θ2 and the time. And by using the definition, it will be the derivative of θ1 with respect to time times the partial derivative of the Lagrangian with respect to θ1 dot plus the derivative of θ2 with respect to time times the partial derivative of the Lagrangian with respect to θ2 minus L. This is L, and the derivative of the Lagrangian with respect to θ1 dot will be the generalized momentum p θ1 equal to n1 L, the derivative of theta 1 with respect to time, and the partial derivative of L with respect to theta 2 dot will be the generalized momentum P theta 2 will be this one. Now substituting this in here and L, we will get the Hamiltonian. This is the full Hamiltonian of the system. Look, there is total full expression, non-linear full expression. And in this case, the Hamiltonian is a conserved quantity because the Lagrangian and the Hamiltonian does not contain time dependency, explicit time dependency. So the Hamiltonian conserved and the total energy will be of the system will be constant, of course. The Hamiltonian equation of motion are given here. Equation 13 and 14. Equation 13 and 14 shows the Hamiltonian equation of motion. Using these equations, we will obtain the evolution equations for the first and the second pendulum. These equations I obtained and I did the derivation using the Lagrangian in a previous video, so it's the same equation, of course. Now, using it is important to use in the case because I will try to show you the numerical solutions for the energy and the theta 1, the evolution of theta 1, theta 2 in the next video on this one. And it is important, it is useful to make all these equations dimensionless. And I will do this equation dimensionless using the parameter time, the dimensionless time tau. Tau will be the time equal to time t divided by capital T, where capital T will be equal to square root of g, acceleration of gravity, divided by L. Using this dimensionless quantity, we will obtain these equations, equations 17 and 18, which are equal to this one. The difference is instead of t will be tau squared, and now will appear these two parameters, alpha and beta, where alpha, look, alpha is equal to n2 divided by n1, the relation between the masses, and beta will be a parameter related to the force, the relation, the force or the elastic force K times L divided by the weight n2 times G. Of course, in this we need to make dimensionless the energy. The energy will be, the dimensional energy will be E divided by K times L squared. This system equation can be made transformed into a first order system. This is two equations of second order system. I will transform this into four equations of first order system, first order system, ordinary differential equation, using the definition theta 1 equal v1, the velocity theta 1 dot equal to v1 and theta 2 dot equal to v2. Using this definition, we will obtain this equation. We know, let's move on. I would like to show you the energy distribution. This is my main idea today. The energy distribution in this case will be the addition of the energy of the first pendulum plus the energy of the second pendulum plus the energy of the coupling. And just recently I read a paper by Sousa, Marcus, Calda, and Viana, and they presented this new approach in which they consider the changes in energy in nonlinear system. And the approach basically consists in describe the system in terms of the energy of each component and the coupling. And the very important point is the coupling. And in this case, we can make this is very easy because the energy of the first pendulum will be the kinetic energy of the first pendulum plus the potential energy of the first pendulum. The energy of the second pendulum will be the kinetic energy of the second pendulum plus the potential energy of the pendulum and the energy of the coupling will be the energy of the spring 1 divided by 2 times k times L squared times sine of theta 1 minus sine of theta 2. And these are the energy distribution in this case. In the next video, I will show you the solutions, the numerical solution for this problem, and the evolution and how the energy changes occurs in the process.